Welcome to this rigorous scientific lecture on scanning tunneling microscopy. Today we're going to explore how physicists and engineers transformed the quantum mechanical phenomenon of tunneling into one of the most powerful imaging techniques in modern science. Before we dive into the instrumentation, let's briefly review quantum tunneling. In classical mechanics, a particle cannot cross an energy barrier if it doesn't have sufficient energy. But in quantum mechanics, there is a non-zero probability that a particle can tunnel through a barrier, even when classically forbidden. Here's a schematic of tunneling. An electron with insufficient energy to overcome the barrier can still appear on the other side with some probability. This probability decreases exponentially with barrier width. The tunneling current I is proportional to the exponential of -2 kappa times the distance z, where kappa is related to the barrier height and the work function of the material. The current is proportional to e to the -2 kappa z. This exponential dependence is the key to atomic resolution. Kappa equals the square root of 2 meters phi over h bar squared, where phi is the work function and m is the electron mass. Let's ask a question. Just how sensitive is this exponential dependence? Let's do a back-of-the-envelope calculation to see why this enables atomic resolution. For most metals, the work function is about 4 to 5 electron volts. Let's use phi equals 4.5 electron volts as a typical value. When you plug in the numbers, kappa is approximately 1 per angstrom. This means the decay length is about 1 angstrom. If the distance z increases by just 1 angstrom, the current decreases by a factor of e to the power of 2, which is about 7.4. This is enormous sensitivity. The current at z plus 1 angstrom equals the current at z times e to the -2, which is about 0.135 times the original current. This exponential sensitivity means we can detect vertical changes as small as 0.01 angstroms, which is 1/100th of an atomic diameter. This is why scanning tunneling microscopy achieves atomic resolution. Now let's walk through the actual experimental workflow, starting with tip calibration. The quality of your tip is absolutely critical for high-resolution imaging. An ideal STM tip terminates in a single atom. In practice, tips are prepared by electrochemical etching of tungsten or platinum iridium wire. The apex must be atomically sharp. Tungsten tips are commonly made by etching in sodium hydroxide solution. The etching process creates a very sharp point, but the atomic structure at the apex is somewhat random. Here's a key question. How do you know if your tip is good enough? You test it by imaging a reference surface with known atomic structure. Highly oriented pyrolytic graphite, or HOPG, is often used as a test surface because it's easy to prepare and has a well-defined hexagonal lattice. Gold 111 surfaces are also common standards. If you can resolve individual atoms with good contrast and without double-tip artifacts, your tip is sufficiently sharp. If not, you may need to recondition or replace the tip. Step 2 is vibration isolation. Remember, we're trying to measure distances with angstrom precision. Any mechanical vibration will completely destroy your measurement. A typical STM sits on the pneumatic vibration isolation table. This isolates the instrument from building vibrations, which typically have frequencies from 1 to a few hundred hertz. Building vibrations from footsteps, HVAC systems, and traffic typically have amplitudes of micrometers at frequencies of 1 to 100 hertz. Without isolation, these would completely overwhelm the atomic scale signal. Good pneumatic isolation can reduce vibration amplitudes by factors of 100 to 1000. Additional passive damping stages inside the STM chamber provide further isolation. To verify your isolation is adequate, you monitor the noise floor while approaching the surface. If you see periodic oscillations in the tunneling current, you likely have a vibration problem. Step 3 is measuring current versus distance to experimentally confirm the exponential sensitivity. This is a fundamental characterization that every STM user must perform. The procedure is straightforward. You bring the tip close to the surface until you detect tunneling current. Then you systematically vary the Z piezo voltage, which changes the tip sample separation, and measure the resulting current. When you plot the natural logarithm of current versus distance, you should see a straight line. The slope of this line is -2 kappa. The natural log of I equals the natural log of I0 minus 2 kappa z. This is a linear relationship in the semi-log plot. In a typical measurement, you'll find that the current changes by about an order of magnitude for every angstrom of tip displacement. This confirms the exponential relationship and validates your setup. From the slope, you can extract the decay constant kappa for your specific tip and sample combination. This tells you the effective barrier height. Let's ask, why is this current distance measurement so important? It's not just a calibration step. First, it confirms that quantum tunneling is indeed the dominant transport mechanism. If you saw a different functional form, it might indicate field emission or other processes. Second, if you can measure smooth exponential decay without noise, it demonstrates that your vibration isolation is adequate. Random fluctuations would show up as scatter in this plot. Third, it tells you the dynamic range for constant current imaging. You typically want to operate where the current is sensitive enough to detect atomic features, but not so sensitive that noise dominates. Step 4 is scanning a reference surface. This is where you actually start to generate images and verify that you can achieve atomic resolution. Most STM imaging is done in constant current mode. A feedback loop adjusts the tip height Z to maintain a constant tunneling current I as you scan in the XY plane. As the tip scans across the surface, the feedback loop adjusts Z to keep the current constant. The Z voltage signal becomes the topographic image. The feedback loop is typically a proportional integral derivative controller or PID controller. The parameters must be carefully tuned. Too aggressive and you get oscillations. Too slow and you can't track the surface. For your first real image, scan a surface like highly oriented pyrolytic graphite. If your system is working properly, you should see the hexagonal lattice of carbon atoms. The lattice constant of graphite is 2.46 angstroms. If you can resolve features at this scale, you've achieved true atomic resolution. Common problems at this stage include thermal drift, where temperature changes cause the tip or sample to move, piezo creep, where the scanner doesn't respond linearly, and tip contamination, where atoms or molecules adsorb onto the tip apex. Step 5 is building a theoretical model that links the tunneling current to the local density of electronic states. This is where we connect the measurement to the underlying physics. The key insight is that the tunneling current is proportional to the local density of electronic states at the Fermi energy. This means the STM is not just measuring topography, it's measuring the electronic structure. The current is proportional to the sum over states mu and nu of the tunneling matrix element, m sub mu nu squared, times delta functions that select states at the Fermi energy. The tunneling matrix element m sub mu nu contains the exponential distance dependence we measured earlier. It describes the wave function overlap between tip and sample states. For simple metals with free electron-like behavior, the local density of states is roughly proportional to the total electron density at the Fermi level. So the STM image approximates a contour of constant electron density. However, for semiconductors and molecules, the local density of states has strong spatial variation due to bonding orbitals. The STM can actually image individual molecular orbitals. Let's ask an important question. What ultimately determines the spatial resolution of the STM? Is it limited by the wavelength of the electrons? Unlike optical microscopy, the STM is not limited by diffraction. The resolution is determined by how sharply the tunneling current is localized to the tip apex. The lateral resolution is approximately the sum of the tip apex radius and the decay length. With an atomically sharp tip, this can be well under 2 angstroms. The resolution delta x is approximately r plus kappa to the negative 1, where r is the tip radius, and kappa to the negative 1 is the decay length, about 1 angstrom. This is why having a single atom tip apex is so critical. If the tip has multiple atoms at the apex, you get multiple tunneling channels, and the image becomes a convolution that loses resolution. Step 6 is validating the model by predicting and observing how the contrast changes when you vary the bias voltage. This is a powerful test of whether we truly understand what we're measuring. The bias voltage V between tip and sample determines the energy window of electronic states that contribute to tunneling. At positive sample bias, electrons tunnel from tip to empty sample states. At negative bias, electrons tunnel from filled sample states to the tip. The current is proportional to the integral from the Fermi energy to the Fermi energy plus EV of the sample density of states, rho sub S of E, times the transmission coefficient T of E and V, dE. Different molecular orbitals or electronic bands have different energies relative to the Fermi level. By changing the bias voltage, you can selectively enhance or suppress the contribution from specific orbitals. Here's the prediction. If we truly understand that the STM measures the local density of states, then features in the image should change dramatically when we vary the bias voltage, even on the same surface. Let's consider a specific example. Imaging a semiconductor surface. Semiconductors have a band gap, so there are no states at the Fermi energy. A semiconductor has filled valence band states below the Fermi level and empty conduction band states above. The Fermi level sits in the gap where there are no states. At negative sample bias, electrons tunnel from the filled valence band to the tip. The image shows the spatial distribution of valence band states. At positive sample bias, electrons tunnel into the empty conduction band. Now the image shows the conduction band orbital distribution. Here's the remarkable result. The images at positive and negative bias can look completely different, even though it's the same surface. This proves we're imaging electronic states, not just atomic positions. A famous real example is the silicon 7x7 reconstructed surface. This surface has a complex arrangement of atoms with different bonding configurations. At negative bias, certain atoms appear very bright because they have filled dangling bond states near the Fermi level. These states dominate the tunneling current. At positive bias, different atoms appear bright because now we're probing empty states. Atoms in different bonding environments have their empty states at different energies. This dramatic voltage-dependent contrast change validates that the STM is indeed measuring the local density of states. It's not just a topographic tool, it's a spectroscopic tool for electronic structure. To make this even more quantitative, we can perform scanning tunneling spectroscopy, or STS. This is where we measure the current voltage characteristic at a fixed location. The procedure is to fix the tip at a specific location above the surface, turn off the feedback loop, and sweep the bias voltage while measuring the tunneling current. The differential conductance, dI over dV, is proportional to the sample density of states at energy EF plus EV. This gives us energy-resolved spectroscopy. For a semiconductor, the dI/dV spectrum shows a gap region with zero conductance, corresponding to the band gap. Outside the gap, you see peaks from valence and conduction band states. This technique allows you to measure the local band gap, identify surface states, and even probe individual molecular energy levels. It's like having a spectroscope with atomic spatial resolution. Let's do one more back-of-the-envelope calculation to build intuition. How many electrons actually tunnel per second in a typical STM measurement? A typical tunneling current is about 1 nanoampere. This is chosen to be large enough to measure accurately, but small enough to avoid damaging the tip or sample. 1 nanoampere equals 10 to the negative 9 amperes. The number of electrons per second is I over E, which is 10 to the negative 9 divided by 1.6 times 10 to the negative 19. This gives 6.2, 5 times 10 to the 9th electrons per second. So about 6 billion electrons tunnel per second. This is a surprisingly large number given that the current is so small. If your scan takes 100 milliseconds per pixel, then each pixel represents about 600 million tunneling events. This statistical averaging is why we can measure angstrom-scale features despite atomic-scale thermal vibrations. Let me summarize the key insights from this workflow. The scanning tunneling microscope exploits the exponential sensitivity of quantum tunneling to achieve atomic resolution without requiring high-energy probes or complex optics. Careful tip calibration and vibration isolation are absolutely essential. Even small vibrations or tip imperfections will destroy atomic resolution. The current versus distance measurement validates the exponential decay and characterizes your specific system. This is not optional, it's a fundamental check. The STM images electronic structure, specifically the local density of states, not just atomic topography. This makes it a spectroscopic tool. Voltage-dependent contrast changes provide powerful validation that we understand what we're measuring. Different biases probe different electronic states. The STM has enabled numerous applications beyond simple imaging. Researchers can use the STM tip to deliberately move individual atoms and molecules, creating artificial nanostructures atom by atom. This has led to quantum corrals and molecular devices. Scanning tunneling spectroscopy allows measurement of local band structure, superconducting gaps, and magnetic properties with atomic resolution. The STM can image chemical reactions happening on surfaces in real time, providing unprecedented insight into catalysis and surface chemistry. The invention of the scanning tunneling microscope earned Gerd Binnig and Heinrich Rohrer the Nobel Prize in Physics in 1986, just 5 years after they built the first working instrument. The STM enabled the entire field of nanotechnology by providing the ability to see and manipulate matter at the atomic scale. Before the STM, atoms were mostly theoretical objects. The success of the STM inspired a whole family of scanning probe microscopes, including atomic force microscopy, magnetic force microscopy, and many others, each probe's different physical properties. Today, the STM remains an essential tool in condensed matter physics, materials science, and surface chemistry. New discoveries continue to be made with ever more sophisticated STM techniques. The scanning tunneling microscope is a beautiful example of how a fundamental quantum mechanical principle can be transformed into a practical measurement technique through careful engineering and deep physical understanding. Building a working STM requires knowledge from multiple domains: quantum mechanics to understand tunneling, electronics for sensitive current measurement, precision mechanics for vibration isolation, and computation for feedback control and data processing. The key insight was recognizing that the exponential distance dependence of tunneling current, which might seem like a nuisance, is actually a gift. It provides the sensitivity needed for atomic resolution. In this lecture, we walk through the complete experimental workflow: tip calibration, vibration isolation, current distance characterization, reference surface imaging, theoretical modeling of the local density of states, and validation through bias-dependent measurements. Each step builds confidence that we truly understand what we're measuring at the atomic scale.